Now we are going to derive an expression for the capacitance of a parallel plate capacitor filled with vacuum. So look at the diagram. There are two parallel metal plates and they are named as A and B. They are separated by distance small d. Positive charges are present on the plate A, while negative charges are present on the plate B, and Q is the quantity of charge on either plates. Now there is an electric field in the region between the two plates, that is region 3, and there is no electric field in the region 1 and region 2. This as a consequence of Gauss Law. See, from Gauss Law we have studied that in the region 1, which is outside the plates, so the electric field is equal to what? Sigma by 2 epsilon naught minus sigma by 2 epsilon naught, and that is equal to what? 0. And in region 2, in the region 2 below this plate B, here also what? This is equal to sigma by 2 epsilon naught minus sigma by 2 epsilon naught, and this is equal to 0 as a consequence and application of the Gauss Law. Now only in region 3. So where is the region 3? In between the two plates A and B. So in region 3, the electric field will be equal to what? Sigma by 2 epsilon naught plus sigma by 2 epsilon naught, and that is equal to what? Sigma by epsilon naught. Therefore, the electric field E is equal to sigma by epsilon naught. So this is the expression for the electric field. Normally, the electric field in between the two plates only will be uniform, and slightly at the end of or the edge of the two plates, the electric field lines will be slightly curved practically. But this effect is called as fringing effect. Fringing effect. Now comparing to the area of cross section of the plates, okay, area of cross section of the plates, the distance between the two plates will be very, very small. In such a case, the fringing effects are eliminated. We can ignore them, and we can assume as if the electric field E equal to sigma by epsilon naught is uniform everywhere inside the space between the two plates. Also, what is the medium which is considered by us here in this case is vacuum. So the medium intervening between the two plates A and B is vacuum. Okay. So the electric field E is equal to sigma by epsilon naught, and this is equation 1. Now electric field E is also equal to the potential difference between the plates V divided by the distance between the plates D. Okay, therefore I can take a potential difference V is equal to E into D, or V is equal to, instead of E, what I am going to substitute? Sigma by epsilon naught. So sigma, so this will become sigma into D divided by epsilon naught. What is sigma here? Already we have heard about sigma. Sigma means what? Surface charge density, is it not? You see here, sigma is equal to quantity of charge divided by area of the plate A, and this is the surface charge density. Or from this equation, what is a Q? Q is also equal to what? Sigma into A. Okay. So from the definition of surface charge density is equal to charge per unit area, Q is also equal to what? Sigma into A. Okay. Now what is the expression for the capacitance of a capacitor? We have defined earlier. Capacitance C is equal to Q by V. Okay. Now the capacitance C is equal to, so C is equal to Q divided by V. So we will substitute. Say for example, this is equation 3. From equation 3, what is the Q equal to? Sigma A. So I am going to substitute here. So this is equal to what? Sigma into A divided by, from equation 2, what is V equal to? Sigma D by epsilon naught. So this is equal to sigma into D divided by epsilon naught. Now sigma is getting cancelled on both sides. This epsilon naught in the denominator, it is coming to the numerator. Therefore, Okay, C is equal to epsilon naught A divided by D. Okay, so this is the final expression for the capacitance of the parallel plate capacitor, and this is equation 4. So what is C equal to now? Epsilon naught A by D. Now on the right hand side, the three factors are epsilon naught, then area of the plates A, and the distance between the two plates is small d. So these are the three factors on which the capacitance of a parallel plate capacitor depends. So the factors, so on which factors the capacitance depends upon is the first one. We can say the area of the plates. The capacitor depends upon what? Area of the plates of the capacitor. And the second factor is what? It is depending on the distance. Okay. So distance between the plates. That is the second factor on which the capacitance depends. And what is the third factor here is that epsilon naught. That is the medium. So nature of the medium. Nature of the medium. Here the medium we have considered is what? Vacuum. Even in place of vacuum, if you take air also, the same formula only we are going to derive, because epsilon naught means what? It is the permittivity of a free space or air. Both are having the same value. So the factors on which the capacitance of a parallel plate capacitor depends are the area of the plates directly. Okay, C is directly proportional to the area of the plates, and it is inversely proportional to what? The distance between the plates, and it also depends upon what? The nature of the medium between the two plates. Okay, up to this I hope you must have understood. Next, what we are going to do is, in place of vacuum, what will happen to the capacitance if any other medium, a dielectric medium, is introduced between the plates? Okay, have you all noted all these points? Shall I go to the next topic? I will rub the board and go to the next topic. Okay. Now let us derive an expression for the capacitance of a parallel plate capacitor with dielectric between the two plates. Okay. So these are the two plates A and B as usual. D is the distance of separation between the two plates, and Q is the quantity of charge present on either of the two plates. Now, the entire space is occupied by a dielectric. The entire space between the two plates is occupied, so that the thickness of the dielectric is equal to the distance between the two plates D. Before introducing this dielectric, the electric field, that is, in the absence of the dielectric, the electric field initially was E naught. So I have written E naught is the electric field without dielectric. Similarly, the potential difference before introducing the dielectric was V naught. I have considered V naught is the potential difference without the dielectric. Understand? So what should be the expression for E naught? E naught is equal to what? Sigma by epsilon naught. Okay, it was the electric field before introducing the dielectric. And V naught, the potential difference must be equal to what? E naught into the distance between the two plates. So this is equal to what? Sigma D divided by epsilon naught. Understand? Therefore, what is the capacitance? I will take the symbol C naught. The earlier derivation we have done, is it not? So that is represented with the symbol C naught, which is the capacitance of the capacitor without the dielectric. And this is equal to epsilon naught A divided by D. So this already we have derived. This is the capacitance of the parallel plate capacitor in the absence of a dielectric. Now in such a situation, when I will introduce a dielectric material medium in between the two plates, the electric field cannot have the same strength. The strength of the electric field will actually decrease. So now the new electric field is denoted with the symbol capital E. So E is not equal to E naught. Understand? So E is the electric field between the two plates when there is a dielectric material introduced between the plates. Similarly, the earlier potential difference was V naught before introducing the dielectric. Now after introducing the dielectric, what is the new potential difference? It will also change. because when the electric field changes, the potential difference between the two plates also will change. And what will happen to the dielectric? You see that already there is a positive potential for the plate A, and this will induce some negative charges inside the dielectric due to polarization, is it not? Similarly, these negative charges of the plate B will induce positive charges, okay, on the other side of the dielectric. As a result, one end will possess minus sigma and the other end will possess plus sigma due to P for polarization. These are the charges which are induced on the surfaces of the dielectric. As a result, a surface charge density is acquired by the dielectric due to the phenomenon called polarization. In the previous video, we have described that only. So, when a dielectric material is placed inside a electric field, means then on the surface, the two end surfaces of the dielectric will be induced with the opposite kind of charges. So, you can see here minus sigma P on the top end and plus sigma P on the bottom side of the dielectric. These are due to the induced charges. So, the new electric field. So, I will write the new electric field E will be equal to sigma minus the polarized sigma P divided by epsilon naught. Okay. You see that the earlier electric field was what? Only sigma by epsilon naught, where sigma is called the surface charge density of the plates. But now since a dielectric is introduced between the two plates, the two surfaces, the top and bottom surfaces of the dielectric will be induced with some surface charge density minus sigma P at the top and plus sigma P at the bottom. Therefore, the new electric field must be equal to sigma minus sigma P divided by epsilon naught. So, this I will consider as equation 1. Since the electric field is changed after introducing the dielectric, the potential difference also will change, and this is equal to what? E into D. E into D. Substituting for E, V is now equal to sigma minus sigma P, okay, into D whole divided by epsilon naught, and this is equation 2. So, the expression for the new potential difference V equal to what? Sigma minus sigma P divided by epsilon naught into D. Okay. So, we are going to now discuss some important points. See, this sigma P, the induced surface charge density will be less or more depending on the strength of the actual original electric field E naught applied. That means this sigma polarization is directly proportional to the original electric field. Because of the original electric field only, the induced charges are produced. Understand? Therefore, sigma P must be proportional to E naught. As a result, the sigma P must also be proportional to the original surface charge density also. Understand? So, since sigma P is proportional to the original electric field applied initially, this must also be proportional to the original surface charge density of the two plates of the capacitor. Or I can conclude from these two, that is sigma minus sigma P also must be proportional to sigma. The difference in the surface charge density also depends upon the original surface charge density sigma. Or once again, this sigma minus sigma P is equal to a constant times sigma, and that constant is denoted with the symbol 1 by K. The constant is denoted by what? 1 by K, where K is also denoted as epsilon R. K is also denoted by another symbol, that is epsilon R, and that is called by two names. One is called as that is dielectric constant. Dielectric constant. And the other name is relative permittivity. Relative permittivity. We are going to discuss at the end once again. So, what are the two names for the constant K, or otherwise equal to epsilon R? It is called as what? Dielectric constant or relative permittivity of the dielectric medium. Okay. So, Now you will see that sigma minus sigma p is equal to 1 by k times sigma. In the equation 2 for potential difference, I am going to substitute for sigma minus sigma p in the numerator. Therefore, what is now new expression for V equal to, you substitute for sigma minus sigma p, what you will get? Sigma by k. So this is equal to sigma by k is the first factor. Okay, and what are the remaining factors? D by epsilon naught. So this is D by epsilon naught, and this is equation 3. This is the actual new expression for the potential difference between the two plates A and B after the introduction of the dielectric medium. Understand? So now the new capacitance, okay, the new capacitance is given by, C is equal to Q by V, and this is equal to sigma. Q by A is equal to sigma. Therefore, Q is equal to sigma A divided by, in place of V, I am going to substitute equation 3. So you tell me what is V equal to? Sigma D by K epsilon naught. So this is equal to what? Sigma D divided by K epsilon naught. So which factor is getting cancelled here? Sigma. So sigma is getting cancelled. This K into epsilon naught is coming to the numerator. Therefore, what is C is equal to K into epsilon naught A divided by D. So this is the final expression for the capacitance of the capacitor after introducing a dielectric. So on the right hand side you see that this is equal to K times epsilon naught A by D. But epsilon naught into A by D is also equal to the capacitance of the capacitor without dielectric, is it not? So we can also write this as C is equal to K times C naught, where C naught is equal to epsilon naught A divided by D for vacuum. Okay, for vacuum. Understand? That is, when vacuum was filled between the two plates in the earlier derivation, we have derived that C naught is equal to epsilon naught A by D. And for air, the value of K is equal to 1. And for other medium, this K is always greater than 1. If you take oil or mica or ebonite, if any other medium other than air is filled between the two plates means, then the value of K is always greater than 1. Therefore, the capacitance of the capacitor will be always increasing when a dielectric is introduced between the two plates. Why? Because the value of K, the dielectric constant, is always greater than 1 for any medium other than air. Therefore, what is the effect of the dielectric? The effect of introducing the dielectric is to increase the capacitance of the capacitor. Understand? So, K is greater than 1. Therefore, C is always greater than C naught. So, what are the different factors on which the capacitance of a capacitor depends on? Already I told you that the capacitance of the capacitor is directly proportional to the area of the plates. If large area is there, means more number of charges, more amount of charges can be stored. Similarly, if the distance between the two plates is reduced, then also more quantity of charges can be stored and the capacity will increase. Similarly, by introducing a dielectric also we have found that the capacitance of a capacitor will be increased. Okay, my dear students, once again I will summarize that the expression for the capacitance of a parallel plate capacitor with the intervening medium as vacuum, that is vacuum, no material medium or no dielectric medium. What is the expression we derived was C or C naught is equal to epsilon naught A by D. Suppose if a dielectric is introduced, then what is the new expression for the capacitance? C equal to K times epsilon naught A by D. Okay students, let us see in the next video. Let us consider what will happen if the dielectric is partially filling. In the previous derivation we found the capacitance of the capacitor inside which a dielectric was occupying the entire space between the two plates. Now, we will derive an expression for the capacitance of a parallel plate capacitor where a partially filled dielectric is found. So, look at the picture once again. Here I have considered the two plates as X and Y, which are separated by distance D as usual, and Q coulomb of positive charge is given to the plate X so that its surface charge density is plus sigma, and the surface charge density of the plate Y is minus sigma. And here you can see a dielectric slab of thickness T. So T is the thickness of the dielectric slab, and it is introduced between the two plates. Now the remaining space other than dielectric is occupied by air. I have taken air. Instead of air, we may also take vacuum also, but I am considering this time as air. So air is filling the space on both sides of the dielectric. Okay. Now what is the T? T means what here? It is the thickness of the dielectric slab, and D is the distance between the two plates X and Y. So how much will be the thickness of air column here? That is equal to what? D minus T. So D minus T represents the thickness of air. So the air is filling only in this space and this space other than the space T. So D minus T must be equal to the thickness of air. Now E naught is the electric field inside the air, and E, capital E, represents the electric field inside the dielectric slab. Therefore now what will be the net potential difference between the two plates? The net potential difference between the two plates is given by, it is a product of electric field into distance. Now what is the electric field inside the air medium? It is E naught. So this is equal to E naught is the electric field inside the air medium, and through how much distance it is traveling through air. What is the space? What is the thickness of air? It is D minus T. So through a distance D minus T and plus the electric field inside the dielectric is what? E into how much distance it is traveling through that medium is T. So this is E into T. So this is the expression for the potential difference between the two plates. Understand? And as usual, sigma is equal to what? Sigma is equal to Q by A. Therefore, what is Q is equal to sigma into A. So this is what? Equation 2. So we have got expressions for the potential difference between the two plates and the charge stored on each plate. Therefore, capacitance, now capacitance C is equal to, okay, capacitance is C is equal to Q by V. Instead of Q, I am going to substitute what? Sigma into A divided by, instead of potential difference, what we have to substitute? E naught into D minus T plus E into T. So this is equal to E naught into D minus T. So the denominator D minus T plus E into T plus E into T. Okay, this is the electric field. So this is now equal to, this is equal to sigma A divided by E naught is the electric field. So E naught is the electric field in the presence of air. So this must be equal to what? Sigma. This is equal to what? Sigma by epsilon naught. And I am going to substitute here sigma by epsilon naught into what? D minus T. Okay, plus instead of E, what is E here? It is the electric field inside the dielectric, and this is equal to what? Sigma by epsilon. This is also equal to sigma by epsilon R into epsilon naught. So this is plus, instead of E, I am going to substitute what? Sigma by epsilon R into epsilon naught, because this is also equal to what? Sigma by epsilon naught into epsilon R. Okay, so I have substituted into T. So here this sigma can be cancelled and the remaining terms can be adjusted. So this is now equal to what? This is now equal to A, capital A, divided by 1 by sigma, that is 1 by epsilon naught into D minus T plus 1 by epsilon R into epsilon naught into T. So this is once again equal to what? Capital A divided by this 1 by epsilon naught is taken as a common factor. Here also 1 by epsilon naught, here also 1 by epsilon naught is there. Therefore, 1 by epsilon naught can be taken as a common factor into d minus t. So, into d minus t plus t by epsilon r. So, this is a t by epsilon r. So that this epsilon naught is shifted. So, this is once again equal to what? Epsilon naught a divided by d minus t plus t by epsilon r. So, this is the expression. This is the expression for the capacitance of the capacitor. Therefore, C is equal to epsilon naught a divided by d minus t plus t by epsilon r. This is the final expression for the capacitance of the capacitor with a partially filled dielectric. Okay. Now, what will happen if the entire space between the two plates is filled with the dielectric? If entire space, okay, if T is equal to D, that means the thickness of the dielectric must be equal to the distance between the two plates. That means the entire space is filled with what? Dielectric. So, if T will be equal to D, then what will happen to the capacitance? C equal to epsilon naught into A divided by first term will become what? D minus T will become 0, because both are one and the same, is it not? So, I will take the first term as 0 plus here this T is nothing but D. T is equal to D, distance between the plates, divided by epsilon r. Therefore, C is equal to what? Epsilon r into epsilon naught A divided by D. But epsilon r is also equal to K, which is equal to what? A dielectric constant. So, this is equal to what? K is equal to what? A dielectric constant. Okay, dielectric constant, and therefore C is equal to K times CO. The same expression we have derived the previous discussion also. So, K is equal to 1 for air. For air, what is what? K is equal to 1, and for any medium, any other medium than air, K is greater than 1. Therefore, C is greater than C naught. Okay. So, what is the effect of the dielectric placed between the two plates? When a dielectric is introduced either partially or fully between the two plates, the capacitance will increase. Have you all understood? So, after this, we will be studying another video on that is the energy stored between the two plates of the capacitor, and then we will be solving the numerical problems. Until then, bye.